in JavaScript, the control flow is not just driven by if then else and calls, but there are also events. And what are events? So this is when, for example, the user presses a button in the web browser, or more commonly in Node.js, for example, when you have an I/O operation that completes. So this leads to asynchronous control flow. And that means we have kind of a new source of bugs that can occur in these programs. So just a brief recap of what is Node.js. So the idea behind Node.js is that you want to write JavaScript applications that run not only in the browser, but also on the server side. So this allows you to use JavaScript as your as a regular programming language where you have access to the file system and operating system facilities and so on. And it's built on the V8 JavaScript engine, and it's hugely popular. So there's this Node repository of packages. It's recently become the largest package repository in the world, surpassing CPAN and Hackage and so on. And there are more than 250 packages added every day. Okay, so let's just look at a simple example of an event-driven Node.js application. So here we have an object which is a chat room. And here we're registering a listener on this chat room. So specifically we have a base object, and we're saying that when we get the event message, then we want this function here that takes 2 parameters to execute. And that function is just going to print to the console that some user says something. Now to send this event asynchronously, we have an emit expression that looks something like this. So again, we have the same base object, we have the message, the string message, and then we can pass some parameters which are sent to the listener. Okay. And then this listener is executed at some point in the future, asynchronously. So what can go wrong in these applications? Well, here are 3 examples taken from the StackOverflow website of real issues that users have encountered and posted and asked, like, why does my program work? So in this case, the user is using the file system module of Node.js, and he has 2 operations. So he wants to rename a.txt to b.txt, and then he wants to perform a stat operation to get the size of the renamed file. So the problem here is that there's actually no guarantee that the rename operation will complete before the stat operation. So you can get an error where the b.txt file does not yet exist. So what the programmer should have written is something like this, where to the rename operation he gives a callback which is executed when the operation completes, and then he can do another callback where he gets the file size. As another example, here is a usage of the socket.io library. So this is a library that allows you to communicate from the server side with the client side, like, for example, the web browser. And so this is the server-side code. So here the user is saying that, okay, he wants to wait for a connection from the browser, and then he registers this callback in here, and then he wants to wait for my event. So my event is something he expects to be emitted on the browser side, and then he just wants to log some data. But when he runs this code and sends the event from the browser, nothing happens. So what is the problem here? The problem is that he registered the listener on this object IO, but this is actually the wrong object to register this function on. He should have registered it on the socket object. So this is dead code. As a third example, here is here he's using the network library to create some server listening on some port. And he passes in a function and that takes a socket, and then he's waiting for the connect event, and then when that happens, he wants to register another listener to wait for some data to come in over the socket. The problem here is that something actually happens implicitly. So the function, the outer function here that's passed in, is actually registered by the call to create server for the connect event. So that means that this function here is actually waiting for the connect event. And so when the connect happens, this code is evaluated, and then he registers a listener for the connect event. But that event was just fired and never happens again. So again, we have this problem that this code here is dead. We have a dead listener, and in this case, it's because the registration happens too late. So what the programmer should have wrote here is simply that he should have not do this registration here. It's already done for him. So these are 3 examples of some of the issues programmers run into. Okay, so in this work, we tried to kind of capture the semantics of Node.js, so we looked at some of the documentation to try to figure out kind of what's going on. And so these are some of the design choices that are kind of made by the Node.js developers. So one is that it's not a multi-threaded system. Execution is single-threaded, and an event listener will run to completion before another event listener can be scheduled. Event listeners are functions that you attach to an object, and you assign some event that it's waiting for, and that event is typically just a string. And you can have multiple listeners for the same event if you want. So what we did was we took the formal semantics, Lambda.js by Guha et al., and then we extended it, adding 3 new terms to the syntax. So one is to register listeners, so you can register a listener on some base object, and the event you register it for is tau, and then you give the function expression. Similarly, you have emit, which schedules all the registered listeners for execution at some later point asynchronously. And finally, we introduced this interesting event loop. So that's a term that signifies when the call stack is empty. So essentially, when you have this, that means that now you non-deterministically select some event listener and execute that. Okay. So let me take a step back and think about, like, when I'm writing a program and I'm trying to understand what the program does, then there's this notion of call graphs. So this is some kind of artifact you can obtain for your program. And the call graph tells you stuff like, if you have a function you're wondering, well, who calls me? Well, I can look at the call graph to see who my callers are. And I can also see from the call graph who I'm calling, right? So this is useful information for the developer, but it's also often used, inside static analysis tools. And let's see what happens with the call graph when you have kind of these kinds of event-based systems. So here we have the event loop, and the event loop just calls all these asynchronous listeners. So if I see that G is called, and I ask, like, why is G called, then I'm told that, well, it's called from the event loop. But that's not really what I want to know. I mean, it does tell me it's an event listener, but it doesn't really explain what caused its execution. Some information is missing. So what we did was we extended the notion of call graphs, and we introduced something called the event-based call graph. So it extends a traditional call graph by adding 3 new types of edges. So one extension is a listen edge that captures a registration. Another is an emit edge that captures when an event is emitted. And then we have this happens before a relation between emits and listens. So just to give you an example, here we have a very simple program. We create an object, then we register a listener for it. So lambda1 is the listener, and tau1 is the event, and then we emit that event. So the event-based call graph for this small program has a listen edge from line 2 going to lambda1, saying that at line 2, lambda1 is registered. It has an emit edge from from line 3, saying that on line 3 the event is emitted that hits lambda1, and it has a happens before edge saying that line 2 happens before line 3. So this is important because it has to be the case that the registration happens before the event is emitted. Otherwise, we get into a situation where, well, if this edge was reversed or didn't exist, then the listener is not executed. So kind of intuitively, in a correct program, we would expect to have these kind of triangle diagrams. So any deviation from this is probably a bug. And I'll get back to that. So what kind of bugs can we find with this event-based call graph? So one thing is, of course, we can provide it like the call graph just to the developer, so he can look at it and see if it is what he expects. But we can also use it to look for dead listeners, so listeners that are never executed, and dead emits, so emits that have no effect. You emit an event, but it doesn't hit any event listeners. So that's likely an error. Okay. So then the question is, I mean, that's nice, but how do we get this event-based call graph? And our idea here is to use static analysis. So you want to compute a safe approximation of the event-based call graph. And then the question you run into is, well, how should you model the event loop such that the event-based call graph you end up computing is actually precise? So we looked at three kind of context sensitivity policies. One is a baseline, which is what's been used kind of in previous work, where you just say, I collect all the listeners, and I just execute them all in any arbitrary order. So this is sound because you get all possible interleavings of the listeners. But it's not very precise, because if there was some dependencies between listeners, that's not captured by that abstraction. The two others we looked at are the event-sensitive one. So the event-sensitive analysis is kind of the obvious thing to do. So you just have a context for all seen events. But the number of seen events can be exponential, the subset of all seen events. So we had some concerns about this being expensive. So we came up with a different type of sensitivity where we separate contexts based on the set of currently registered listeners. And just as a side note, these two are incomparable in precision. So it means there are programs for which this is the better choice, and there are programs for which this is the better choice. So it's not like one subsumes the other. Okay, let's look at a small example to see how these three things work. So here I have something I met is maybe like a file object. I'm registering a listener for the open event. And then when that happens, I'm going to register a new listener for the data event. And then I emit the data, and the whole thing starts when the open event is emitted. So kind of intuitively what happens is that if you have the baseline analysis, you just have the event loop represented as a single node. And there is no ordering between open and data listeners. So you just go into the same loop. The event-sensitive version, on the other hand, has three states. It unfolds the loop into three states. One is where you have seen no events, then you have seen the open event, and then you have seen the open and data event. So this allows you to know that the lambda open is always executed before lambda data. And finally, the listener sensitive is sort of similar, but instead, remember, it records the set of currently registered listeners. So once you enter the event loop, well, this listener was registered. So that's what is in the first state. And in the second state, another listener is registered. So this also separates the data flow, but has one less state. Okay, so we implemented this in a static analysis tool. The tool is similar in spirit to TA.js and JS AI in the sense that it's a points-to analysis. It's a flow-sensitive points-to analysis. And it also has data flow analysis, and it does call graph construction on the fly, also this event-based call graph. So it's an expensive analysis. When you have to do points-to analysis that's flow-sensitive, it's expensive. But we have to do it because we need to reason about objects, as you saw in how these events are used. Okay, so we considered two questions for the evaluation. So one question is, can we actually use these techniques to find, like, can we use the event-based call graph to find bugs and to understand the bugs? And then we considered, like, we have three analyses. How do they compare with respect to precision and performance? So we went on StackOverflow, and we found 12 program fragments, so real code that was posted by someone else, typically like saying, well, here's my code of the relevant fragment. I expected this behavior, but instead I get this. Why? So these programs all had one bug in them, one event-related bug. And then we took three larger programs that are correct from the Node.js documentation and the Node.js book. So we used the StackOverflow questions to answer the question of, is this useful for finding bugs? So in this table here we have the question numbers, and then we have the three analyses. And so the original column means that we took the original code and ran the analysis on it, and did it report an error. So since all three analyses are sound, it's just kind of a simple check. Like, we expect all analyses to find, all the errors. Okay? So we see that. So all analyses report an error for the original buggy program. But then the question is, what happens when you take the buggy program, you make a small change, so now it's correct? Well, then the error should go away, right? You don't want to have, false warnings. But we see here that the baseline analysis, because it cannot separate data flow in any meaningful way in the event loop, for 5 out of the 12 questions, it still reports the same error. So even though you fix the program and it's correct, it still says, well, there could be a dead listener. On the other hand, both event and listener-sensitive analyses they don't report any spurious warnings, as you can see in these two columns. Okay, so that's good. But the question is, how well do these things scale? Right, okay, so the baseline has spurious warnings. So here are the 6 correct programs that are somewhat larger. And to explain one, let's say we look at this HTTP example program. So the baseline analysis reported 10 dead listeners. And I didn't talk so much about this, but it computes this may happen before relation. And the smaller that relation is, means the more precise your analysis is. So in this case, it has 66 edges, and it took this amount of time. The event sensitive timed out for this benchmark. The listener sensitive reports 0 dead listeners, and it has a may happen before relation that has 41 edges, and this is the time it took. Okay. So one thing we immediately see is that event sensitivity has poor performance. It doesn't scale even to these fairly small programs. And that's because it has to track like an exponential number of seen events. And often it's the case that when you have like a file stream or a socket or something like that, then you can see many different events. Like the next event could be a data event, it could be an error event, it could be a close event, stuff like this. And then you get all these possible interleavings it has to track separately. Yeah, so this was kind of expected. We do see that using event and listener sensitivity improves flow sensitivity because they may happen before relations are smaller than the baseline. So you do regain some flow sensitivity by unfolding the loop. And yeah, finally, kind of the conclusion is that the listener sensitive analysis reduces the number of spurious warnings significantly. So it only reports, like 5 in total compared to, I think this is 44 or something. All right. So in summary, right, so the first question was like, are these things useful to find bugs? And yeah, I mean, the 3 analyses are sound, so they do report the bugs, but it's only kind of the listener and event sensitive that, doesn't report any bugs on the corrected programs. And yeah, event sensitive, I kind of already talked about this, so let's just continue. So some people might ask, well, how does this relate to events in the browser? Because I only talked about Node.js. And I think there are 3 challenges to handling events in the browser. So the first challenge is that in the browser you have the HTML page. And so that means you need some model of the HTML page and how event listeners are attached to this, to the page. The second thing is that events are more complicated in the browser because you propagate events along the structure of the page. So you need some model, and then you need to propagate events along the structure. And then the third thing is, like, how should you then separate data flow based on listeners and events and so on? And this work, we've kind of only focused on this challenge because this is what's relevant for Node.js. If you want to do event stuff in the browser, you need to also consider these 2 challenges. Okay, so in conclusion, events can be a source of bugs in JavaScript programs. We've introduced the event-based call graph as an artifact to understand the control flow in your program, but also to look for bugs. We evaluated these 3 context-sensitive policies, and the listener sensitivity analysis has significantly better precision than the baseline at a modest increase in analysis time. Thank you. That's my talk.
Thank you, Magnus. Questions?